All right, so we left off last class. Where this from? It's still happen. So last class we left off looking at contingency tables. From last class, I put up the next Connect and Excel homework. I think originally the syllabus said we'd have an exam at the end of next week. It's probably going to get pushed off another week like that. I think it's October 1st, is that Friday? Just give us a little bit more time. We can cover the rest of the material that we need to before that exam. So you'll have those two assignments that'll be due about 2 weeks from yesterday. So I start working on those early so that as we get closer to that exam, we won't have to worry about those. You can kind of transition to looking at some of the practice exams I'll be putting out. So we left off, sorry, any other questions from me before we kind of jump in? Yeah.
The exam, is that over next Friday or is that in class next Friday?
Yeah, so we're going to do in-class exams. Like I just said, we're probably going to push it forward a week. So it'll end up being October 1st instead of 24th. I was a little overzealous with my my choosing of the date. But we're kind of making pretty good progress on the material, so I would expect it to be that Friday, October 1st. Any other questions for me before jumping into things? So last class we talked about looking at the union, and I can show you. Okay, we have this typical way of thinking about something's an A or B. Oops. I'll go back here. All right. I thought about, we had this definition that we just add the probability of the two things together and then subtract what we double counted, which was the intersection of those two events. We could get the union. That was how we were thinking about it last class, right? And we could grab those things pretty easily from the contingency table. Probability of A is 0.6, probability of B is 0.5, probability of the intersection right here is 0.4. There's another way we can think about the union. It's a very non-technical way, but I'll show you why it works. If you are looking for the union of two events, if you just go to their intersection and kind of make an L and add those values up, you'll actually end up finding the union as well. So 0.4 plus 0.2 plus 0.1 gives us that same 0.7 as the method we left off on last class. So why does that work? So think about it, I've got event A and event B. I could break this down into three components. Okay, so do that for it. We think about everything that's in this kind of crescent moon, right? We can come up with what that is here by thinking about all these outcomes are in A, but notice they're not in B, right? They're outside of B. So really all this is the intersection of A and not B. Well, not B is just B complement. We then got this kind of crescent moon over here. These are all the outcomes that are in B, but notice they're not in circle A. This is just everything that's in A, not A, sorry. Everything that's in B and not in A, well, not A is just A complement. And the last kind of area we have here is what's in all the outcomes that are in both of these circles, right? Where A and B overlap. Well, those are just all the outcomes that are in A and in B. So if we think about, I just add up each one of those areas, the red plus the black plus the green area, that fills out the entire space of both of those circles, which you said what that represents, right, is our union. We go back, there we go, right? This white area, the area in both of our circles or both of our events, that just means is the outcome in A or is it in B? Add these three things up. Notice the probability of A and B complement right here. The next thing we had was add the probability of A and B. Next thing we had over there was the probability where B and A complement. So that's why kind of that non-technical way of, I'm looking for the union, just look at the intersection of the table, make an L and add them up. Well, that's why it works. The way that this contingency table is set up, it'll always kind of give you those three components. Okay? questions on that? I would probably stick to this way, just because it's a useful equation for some other things that we'll even do today. And I think it's just intuitively a little easier to think about, but just take each area, each probability, add them together, and then just subtract out what I double counted, which is what's in both of them, right? The intersection. There's another way of kind of thinking about it. So something that we could see with two events is that they happen to be mutually exclusive. I might have already used this terminology when we were talking about creating bins. But the idea of being mutually exclusive just means that you can't see these two things happen at the same time. So if we're thinking about this in general terms, right, events A and B, that would mean I could never see an outcome that's in A and in B. So what does that mean about my circles if I'm thinking about the visual? If there's no outcome that's in both of them, the circles would not overlap. There's nothing that's in both of them, so there's literally no overlap, or it looks something like this. There's no overlap between those two events, so the intersection is just 0. If I can't be in both A and B at the same time, then what's the probability of A and B? What can occur? The lowest probability we can ever see is 0. So we've got the intersection of the two events being 0. That makes this kind of addition rule, or not addition. This makes the finding the union a little bit easier, right? Because now if I subtract the probability of the intersection, well, the probability of the intersection is always 0 for mutually exclusive events. Subtracting 0 doesn't change anything. I can almost just ignore that. That's just because the intersection doesn't exist if they're mutually exclusive. In a contingency table, what would that look like? We'd have to see something like 0. Also, there's a small typo here. I forgot to update. This total should be 0.7. Right? Because we should be adding across the rows and down the columns. Like I can't copy and paste an old contingency table, change it to 0, and I thought I'll update everything we did. But kind of the main takeaway here is the mutually exclusive, we'd end up seeing a 0 there for one of those top 4 left cells, right? Because that intersection should be 0, right? Maybe it's not A and B that are mutually exclusive, maybe it's A and complement or whatever happens. Any questions on this one? It shouldn't be too bad. Just kind of a definitional thing. So I just used the example of, the 90s phone internet access were mutually exclusive. Had one phone line, you either had to be using internet or you had to switch off the internet to use the phone. Right? None of you probably remember this. I got yelled at plenty in high school for this, so this is why I use the example. Okay. So we're going to take it one step further, right? If we know how to find this union, there's actually going to be another equation we know has to hold. Okay? So if I'm thinking about this visual, if I took the area that's white and added that to the area that's blue, that is every possible experimental outcome, right? Those two things should add up to 1, right? Because they would fill out the entire experimental outcome space. I think last class I gave you a little bit insight as to why that blue area represents the intersection of the complements. If you think about, that was where I had like the vertical and horizontal lines, and where they overlapped was what was not in A and not in B. If you want to go back and refresh from that, you can, but for now, just, we're going to use that. If you don't remember that, believe me that this blue area represents the intersection of the complements. Okay? What's the area that's in that white area? Those are just all the outcomes that are in A or in B, right? Or they could be in both, but they're in at least one of them. So if we take that white area, A or B, right, or A union B, and we add that to that blue area, which is just the intersection of our complements, we told that, I can break this down because I have an equation that I know will find me the union. That was just take the probability of each event, add them together. And if they're not mutually exclusive, I have to subtract out what I'm double counting, which was the intersection of those two. And then I'll still have this component. I'm trying to see over there, right? I've got the intersection of my complements, that stuff. And now I've got 4 things that I know will always add up to 1. So now if I give you any 3 of these components, you should be able to find the 4th, right? Just a little bit of algebra. So I forgot my clicker over here. But if I had a question like this, and I wanted to find the probability of B, I don't know what it is, but I've got these three other components. Well, the probability of A is at 0.5. Probability of A is 0.5, so I plug that in. I don't know what the probability of B is, that's what I'm looking for. The probability of the intersection is 0.1, and then the probability of the intersection of the complements was 0.3. But once I have those plugged in, it should be, I mean, hopefully it shouldn't be that tough of algebra, right? So I've got what? 1 is equal to 0.5 plus 0.3 minus 0.1 is 0.7. Subtract 0.7 from each side. And I'm left with that thing I didn't originally know, the probability of B has to be 0.3. Now, you could have started out before you plug any of the numbers in. You could have just rearranged this equation for the thing that you don't know. So I think that's what I have here, right? Whoops, up there. I could rearrange that equation so I had the probability of B as a function of these other things, then plug the values in. I honestly think that's a little bit, to me, when you're doing algebra with just letters and things, it's a little bit trickier. So I would probably plug the numbers in and then do the algebra. But either way, should get you that answer of 0.3. Whichever way you find the easiest. But I can probably plug in the and then you have this one thing you don't know. Now rearrange until you have it. Questions on? Shouldn't be too bad. So if we use that same equation and we had another kind of missing value, we could find that as well. So I'm going to give you a couple minutes to kind of work on this one, work with the people around you if you want, talk about how you solve this. All right, we know we have this equation with these four components that up to 1. If we're given 3 of them, we should always be able to find the fourth that we don't know. Here, the one we don't know is the probability of the intersection of these two things. Okay, but if we have the probability of the intersection of the complements, we have the probability of each event, right? We should be able to solve this one. Okay, so I'll give you a little bit of time to work on this.
Have you put it on here so we're able to join? Have you put it on here so we're able to join the class?
I should be able to. Is it not showing up? For the virtual, you mean?
I'm sorry.
Are you talking about like a virtual app? It should be open. Is it not showing up there? All right, let me try restarting the app then. I'll try restarting it. Section 3. All right. All right. Give me another couple minutes to work on this. Can you guys see that over there? Okay. Can you guys see that over there? Okay. Yeah. Okay. No, okay. Go to the 2:30 marks, another 25 seconds or so. All right. If you haven't gotten an answer in, take your best guess. It's like we got 30 of us here, 31, 32. Anybody need a little bit more time? All right, I'm gonna close it out. All right, so what answer did you guys get? Yeah, 0.1. So really, it's really the exact same cost as what we just did over here. We're just gonna have different values, right? It's the same equation. So we've got what? The probability of A is 0.3 plus the probability of B is 0.3. We don't know the intersection. The probability of the complements was 0.5. Now at this point, it could be a little tricky, right? Because we've got that negative sign floating around there. But if you think about 1.1 minus the intersection, if we don't even worry about algebra, right? If I've got 1.1, what would I have to subtract from it to get me 1.1, right? Now, if we rearrange this, move this to the other side, subtract 1 from each side, we'll end up with 0.1 as well. But even at this point, right, you can kind of see, intuitively think about, well, what's going to have to be subtracted from 1.1 to get me 1. You could have rearranged the equation to solve for what you didn't know, right? We went ahead and did that and then plugged in all the values, still end up with the same answer of 0.1, which is a different, slightly different way of approaching. Any questions on this? And remember, so these things might seem arbitrary, right? We can grab all of these from contingency table, right? Probability of A, 0.6, probability of B, 0.5. The intersection of the complements, 0.3, right? So these are all components that we can find in our contingency table. And use contingency table to do, there we go, an example like this as well. Even if I didn't have the visual, I could grab these values from that table. Okay. Like maybe I leave out like some of the cells, right? So you couldn't see what the intersection is. You could see the probability of A, the probability of B, and the intersection of the complements. You could still come up with that intersection value was. Questions on that before we keep moving? We've got one more thing we'll kind of take a look at, and then we'll kind of transition to doing a little bit of work in Excel, I think, to the time of the class. So the video that I put out there, I said wasn't necessarily had to watch. I'm not going to ask a specific kind of question on it necessarily, but we're going to cover it. So I'll probably go through this a little bit quicker. Was over conditional probabilities. Right? So the idea of a conditional probability, we might start out with this multiplication rule. I think there's an easier way to think about this. So instead, if I rearrange that equation a little bit, so if I'm looking up there, I've got the intersection is equal to this conditional probability times, right, the probability of whatever I'm conditioning on. Remember, whatever's on the right-hand side, that's what we say we're conditioning on. We're given that whatever's on the right-hand side of this vertical line, that has already occurred. So given that A has occurred, what's the probability B has occurred? If I rearrange this equation and just divide each side by the probability of A, I'll get something like this, right? I can kind of solve that equation for the conditional probability, right? Well, now on a contingency table, I can imagine, well, I can find the intersection of two events, and I can find the probability of an event, right? So I can find these conditional probabilities pretty easy. So what do these conditional probabilities represent? So I'll try to give two different ways to kind of visualize this. The first way is going to be one that highlights, well, let me think, let's do maybe a little bit different examples we've done before. So instead of circles here, I'm going to cut the experimental outcome space in half and say that half is event A, such that the probability of A is equal to 0.5. I think I'll save the other example for talking about independence. Let's do that. So then let's say my event B is something like this. Okay. And let's say the probability of B is 0.4. Okay. Well, notice the intersection of A and B is relatively small compared to everything else. I try to draw this somewhat of scope. So let's say the probability of the intersection of these two events is something pretty small. Everybody with me so far? Like I said, usually we've got two circles to make it easier. I'm making event A just half of the experimental outcome space. So when we have these regular kind of the probabilities we've been looking at, I would call this the unconditional probability of event B, right? So the probability of B is the unconditional probability of B. What if I wanted the probability of B, given that event A has already occurred? Okay, so what we would call this is the conditional probability of event B, right? We're still looking for the probability of B. It's just now we're conditioning on A occurring. So all I wrote above here, you can't quite see that. This is the conditional probability of B. That's where we write, we're looking for the probability of B given or conditional on that A has already occurred. So if we think about here, if I know that A has occurred, it's almost like I'm saying, okay, I know none of these outcomes can now be the outcome of this experiment, right? Because given that A has occurred, I know the outcome that has occurred is somewhere in this space. So by conditioning on A, it's like I've taken the entire experimental outcome space of 1, and I've limited it down to just 1/2, right? Only half of the possible outcomes are outcomes I could now see because I know that I'm somewhere in event A or somewhere in this space of A. So all these outcomes are kind of ruled out. So it's almost like instead of this base of 1, my new base is going to be whatever the probability of the event I conditioned on. So, right, the probability of A, my new base is 0.5. Well, now that I know that I'm somewhere in this space, well, now what's the probability that I can see an outcome that's in event B? Well, the only ones where that would be true would be these guys right here. So of this remaining space, after I've conditioned on A, the only outcomes that would then be in event B, right, the conditional probability of B, that's what I'm looking for, are the outcomes that are in both A and B, right? So you can kind of see here, that's going to be a very small area of outcomes. Force myself out of some room here. But I can think about plug in the intersection of A and B, divided by the probability of A. And notice the conditional probability of B is 0.1. The unconditional probability of B was 0.4. So those two things can be wildly different. And why? Well, because if I just look at the entire experimental outcome space, B made up a pretty large proportion of it. But once I've conditioned on A, once I'm looking at this new space, well, B doesn't make up a very high portion of the space of event A at all. Right? So this is kind of why when we condition on other events, we can sometimes end up with very different conditional probabilities. And it makes sense. If you give me some information here, like starting out, I'm running this experiment, all these are possible outcomes. So the only ones that are in event B will be all these, right? But if you told me, okay, given that A, I now know that A has occurred, well, I know that none of the outcomes that are over here in B could now happen, right? I'm only left with a very small number of outcomes that I could still see that are in both event A and event B, right? So it's kind of limited this space down for me. Having more information is always a good thing. Okay? Any questions on this point? So this is the idea behind why that equation is what it is, why the multiplication rule works. Try to give you a little bit of intuition behind that. But procedurally, right, This is just going to be probably grabbing probabilities from a contingency table and being able to solve for this. So here's kind of a sum of all of our rules. We've got the complement rule. We looked at this addition rule for finding the union of two events. We looked at this multiplication rule just now, right? So what if I wanted to find the probability of R1 given C2, right? So the equations that we're going to use, the general form of the equation, I want the probability of B given A. It's going to be the intersection of those two events divided by whatever I'm conditioning on. Right? So I'll give you a couple minutes here, try to work through this one. This is kind of what I went over in that little pre-class video. I said, we'll ask specific questions on kind of setting up this idea of conditional probabilities and how we use a contingency table. So give you a couple minutes to work on this one, see if we can kind of come up with, using this equation, right, what would be the conditional probability be here. See over here. Go for about another 20 seconds or so. We'll kind of talk about it. All right. If you haven't gotten an answer in, take your best guess. I thought we had 34, but I might have been picking up someone from another class. All right, I'm going to close it out. Okay, so I'm wanting the conditional probability of R1 C2, right? R1 given C2. If I have this general form of the equation, I'm going to write it out in the context of my example. So I want to what R1 given C2. That's just going to be the intersection of those two events, so R1 and C2. I wanted R1 given C2. Divided by the probability of what I'm conditioning on. That's what's on the right-hand side of that line. From here, it should be pretty easy, right? If we've been looking at these contingency table examples, what's the intersection of R1 and C2? R1 and C2, 0.2, right? And then what's the probability of C2? Right, 0.5, right? You just go down to that total column. Right, and get that conditional probability. So a lot of the times I think having the general form of the equation is helpful, but instead of just like starting out right, plugging things in, write this out here, then you can kind of think about it. Everywhere where I see an A, I should be putting an R1. Everywhere I see B, I should be putting C2. Any questions on that one? All right, so we got our answer here. The next definition we have is the idea of independence. So I went through, I thought it was a pretty interesting example, but that pre-class video, if you want more work, if you didn't watch it, you want to go back through and see some more examples of work of solving conditional probabilities using a contingency table, you can actually go out and like grab a bunch of the data on vaccines and people dying from COVID. You can kind of play around with the hospitalization. So I think the example I gave you was with deaths, and we define conditional probabilities. So given that you have the vaccine and you get COVID, what's the probability that you end up dying? Given that you have the or didn't have the vaccine and you contract COVID, what's the probability that you don't die, right? Or you do die. So you can kind of compare those two things. I think the example I gave was something like 0.07 and 0.1. So there's quite a bit of a change in the probability of death, almost a 33%. If you want to look at a 25% decrease from kind of the non-vaccinated, but you can play around with the data, full transparency. I think grab the hospitalization data, and even though I don't fall on either side of any debate, I just look at the data, right? And so the death data, I think there was a pretty stark difference. And then if you play around with the hospitalization numbers, it's actually pretty similar between vaccinated and unvaccinated people, which I found kind of interesting. I don't really know what to make of that, but the data is what it is. So another way of thinking about events, like maybe being vaccinated and kind of dying from COVID, are events that depend on each other. But potentially, if it doesn't look like getting vaccinated had a large impact on the hospitalizations, maybe being hospitalized and getting the vaccine are what we would call independent events. Okay? So two things are independent if the conditional probability of an event is the same as the unconditional probability. Knowing that B has occurred doesn't change the probability that A occurs at all, right? So that would be the idea of independent events. So I'm going to try to give you a visual of that. So let's say I've got event A over here, right? So it's the entire space here. So we'll say the probability of A is 0.5, right? It cuts it perfectly in half. We then have event B, and it just cuts the experimental outcome space in half the other direction. So the probability of B is also 0.5. And then I can think about, okay, where's the intersection of A and B? Well, that would just be everything down here. So if I've drawn this to scale, and the idea of what I'm trying to do here is, if they both exactly cut it in half in other directions, then the probability of that intersection would be 0.25, right? So it's going to be that bottom kind of fourth I have here of my entire experimental outcome space. Well, now if I want to find something like a conditional probability, so let's say I want to find the probability of A given B. Right? Well, I'm going to look for the intersection of these two events, right, divided by the probability of one I'm conditioning on, the probability of B here. Well, now I can grab these pretty easy from a contingency table or from my visual here. So the intersection was what? 0.25. The probability of B was 0.5. And I get that conditional probability of A, right? A conditioned on B is the exact same as the unconditional probability of A. So the reason why that can occur is because if we look at the entire experimental outcome space, about 50% of the outcomes are in event B, right? Well, once you tell me, okay, sorry, I'll say it again, because I was thinking I did it backwards. Of the entire experimental outcomes, half of the outcomes of event A, right, or sorry, half the outcomes are in event A. So the proportion of the total outcomes that are in event A is 0.5, 50%. Well, if you then give me this additional piece of information, which is, okay, you're not looking at the entire experimental outcome space anymore because I'm telling you that B has occurred. So once I've conditioned on this other event, well, now if I look at all the outcomes in event B, the proportion of them that are still in A is still 50%. So it's like this additional piece of information didn't change the proportion of outcomes that were in the event that I was looking at. So the idea here might be something like, I always try to choose an arbitrary one. So if you think about the probability and that you could probably tell me a story why this wouldn't be the case, but this is how my mind is talking about it. So if you tell me, if I select a person at random, what's the probability that they're registered Republican or Democrat? Right? So those are your events that you're interested in, right? Well, maybe it's about 0.45 or 0.4, right? Probably if I select someone at random, probably they're a registered Republican, maybe even 0.4. Well, if I then say, okay, given that that person is over 5'6", well, now what's the probability that they're a Republican? Well, it shouldn't change the probability at all. I would assume that the height distribution looks similar between registered Republicans and Democrats. There's no reason to believe that it would necessarily vary, right? So, it's having this additional piece of information that just isn't related, right? Your other variable, your other event doesn't depend on it, right? So if it doesn't depend on it, we say they're independent events. They're independent from each other. Okay? And we could kind of, then substitute in for multiplication rule, just like knowing they're mutually exclusive made finding the union easier. Knowing that they're independent events makes finding the, knowing they're mutually exclusive made finding the union easier. Knowing they're independent events actually makes finding the intersection easier. Because this was our multiplication rule, right? We know that the intersection is just the conditional times what we condition on. Well, if they're independent events, the probability of B conditioned on A is just the same as the probability of B, right? So I can plug that in. And now to find the intersection of A and B, it's just simply multiply the probability of the two events by each other. We don't have to find this conditional probability anymore because if we know they're independent, this conditional probability is just the same as the unconditional. So you can imagine a contingency table. I can check this pretty easily, right? I can go look at the intersection of the two events. I can go to the total columns and find the probability of each event. If those two things aren't equal, they're not independent. But if they are equal, then we would say they are independent. And that's just kind of a byproduct of the definition of what independent events are, which is that the conditional probability is the same as the unconditional probability. Any questions on that before we continue? So if I'm looking at a table like this, and I want to check to see are these two events independent, I can do this a couple ways. So what's one way that I just said I can do it? I don't think I have this way first in the slides, but it doesn't really matter what order we go. So first of all, I just take the actual definition. That the conditional and the unconditional probability have to be the same. It doesn't matter which one of these I choose. I think I'm doing them out of order, but I can't remember exactly, so we'll see. Well, I know that the conditional probability is what? The intersection of those two events divided by the probability of what I'm conditioning on. Because remember, whatever I'm conditioning on, that's my new experimental outcome space I'm looking at. Not one anymore, but the smaller area. For my table, what's the probability of B? Just go down to the total. Someone wanted that thing, 0.25, right? What's the intersection of A and B? 0.15. I just go to that top four left cells, find where A and B kind of relative line up. And then what's the probability of just A? Someone said it, 0.6. 0.15 over 0.6. Actually ends up being 0.25. So because these two things are the same, I would say they're independent events. The conditional and unconditional probability are exactly the same. We could have also checked this. I think, let me see here, I probably did add an A first, so I think I'm the other. Oh, there we go. That's the one that we just did. You could go through and do the same thing to see if the conditional probability of A and the unconditional probability of A were the same. It's the same process. Right, so a little bit different numbers you're plugging in there. Or we have a third way, which I said, just like when it's we have mutually exclusive events, makes finding the union easier. If we've got independent events, makes finding the intersections. So we said the intersection of two events, if they are independent, should just be equal to the product of the each probably of each event. So what's the intersection of A and B? You just said that over there was 0.15. What's the probability of A? 0.6, probability of B, 0.25. And sure enough, these end up working out to be the exact same value as well. I think I have that here, right? Now, so any questions up to this point? So it's different ways of checking for independence using the contingency table. And I don't think I'll dive into this too much today. Maybe we'll revisit it next class if we have time. But one interesting byproduct of two events being independent are that they're complements and they're independent as well. So I could actually check to see if the complements intersection is the same as the probability of each complement multiplied by each other. That's just kind of a byproduct. You can kind of imagine when I had the squares drawn here, if you think about the complements, well, those spaces were still 0.5, 0.5, and their overlap would have been 0.25. So we could go through the mathematical proof. It's not entirely interesting, and I'm not really going to use this idea that the complements will also be independent, but just to kind of mention it here because it goes along with the discussion. So kind of primarily, I would think the easiest way to check to see if they're independent is something like this. But if it's easier for you to remember, well, the definition of independence is that the conditional and unconditional probability are the same, and you want to check it this way using kind of that multiplication rule, that's fine as well, right? All three of them will show you the same thing, that either these events are independent or that in fact they are dependent, right? If those aren't equal, right, we would say they're dependent events. Any questions before we keep moving on? Got a couple of examples we could work through, but 8 minutes. What can we do in Excel? Maybe we'll start Excel. I'll kind of show you how we'll start building our own contingency tables. Okay. So just to kind of introduce this so we don't have to go into it or waste time at the beginning of class. So up on Canvas under files, I've got this union data file, right? So this has a bunch of different industries across several years, right? There's 2 worksheets. One of them says blank, one of them says final complete. So this is hopefully what we'll kind of rebuild. We might even do a little bit more than what's on here, but we'll start with this blank file, okay? So what I kind of started out doing was saying, okay, look, maybe I just wanted to find what the average union membership was across these industries, across these time periods, right? So I've got this variable that represents the percent of that industry that's unionized. So I select that entire variable, hit enter. I've now got kind of the average or mean union membership across these industries is about just under 11%. Right? I'm going to kind of skip these other things for right now, but I could also find kind of what's the average difference in earnings between union and non-union members. So I've got weekly earnings here for union and non-union members. I just took the difference between those two variables, and that's the difference in union, non-union earnings, right? I think it's weekly. So I select that entire kind of variable. So a question I might have here is something like, well, the higher the percent of workers that are union workers, there's less like available substitutes for a company. They can't go out, and hire a non-union worker for a lower wage if there's 100% of the workers are unionized. So the higher the percent of that industry that's unionized, we might see that union have more power and be able to kind of argue for higher and higher wages, and that difference in union, non-union wages would likely go up, right? So we're going to eventually be able to kind of answer or test that idea once we get to the actual kind of data. So I'm not going to use these numbers exactly as my cutoff just because I want to make it look a little cleaner, right? So I'm going to put up my cutoffs up here. I'm going to use 10 and 100, right? So they're close to the mean, and they're going to kind of signal that if I see an industry that has a percent unionized more than 10%, that's kind of a high percentage union industry. And the difference in earnings, if it's more than $100, I'll say there's a pretty big difference in union, non-union earnings. And if it's not, greater than 100, I would say it's kind of a smaller difference. Right? So I set up my contingency table to be interested in these two events. Is the union membership 10% or higher, or is it the complement of that, which would be below 10%? And then is the earning differential $100 or more, or the complement of that is that difference less than 100. Right? So to get my probabilities, right, kind of floating behind the scenes are actually frequencies. Right? So we can start to fill out a frequency table, kind of looks like our joint probability, our contingency tables we've been looking at, but instead of probabilities initially, we'll start out with frequencies. Okay? So one equation that we should have already used on that first Excel, and that we kind of used in our previous Excel example, we're looking at frequency distributions, is this count ifs. Right? Now we're going to use it a little bit differently than how we used it before. So this category, right, or this part of my table represents all the industries that have 10% or higher union membership and $100 or more wage differential between union and non-union workers. So I want to count the number of industries from my data that meet those criteria. So I'm going to go over here. The first thing I'm going to select is this union member percent variable. So Control Shift, Command Shift on a Mac, hit the down arrow. I scroll back up. It'll put in that range for me. Then comma. Well, why do I want to look at that variable? I want to look through it and count the observation only if it's greater than or equal to. And instead of typing in 10 here, I could do that and it'd be fine. But because I have the cutoff values up here, I'm just going to click on the cell that that value of 10 is in. Okay. And then comma. The next variable I want to go through was the one where I'm looking at, is the wage difference $100 or more? So I want to look through this difference in earnings variable. Instead of selecting it, because I have to scroll up every time, I can see it's in column H. I know that it's going to start and stop in the same cell. So I just type in H2 through H736. Okay? Just based off of that first variable, right? I knew where it started and stopped, and my new variable I'm looking through is in column H. So then comma, well, why am I looking at that difference in earning variable in column H? Well, I want to check to see, is it $100 or more? So is it greater than or equal to? Then instead of putting the $100 value in, I've got it up here in a cell to make it kind of easier if I want to make changes in the future. And this should count for me the number of industries in my data set that have 10% or higher union membership and a wage differential of $100 or more. Right? Sure enough, it gets 221. Now I could go through and do this for the other 4 combinations, right? And I'll kind of make sure I actually save this right now. So that next class, that's not where I want to be. We'll kind of pick up where we left off. But one thing that we'll start doing once we start to get the rest of these frequencies, if I know that 221 of the observations in my data set fit this category, how could I turn that into a probability? If I eventually can get the total number of observations that I have, well, then I know that 221 out of, say, 1,000 of the observations fit that category. So if I selected one at random, the probability that it would be in this category would just be 221 over 1,000, right? Over my total number of observations. So we'll work on building the rest of this table out, then getting probabilities next class. We'll probably do a little bit of work, kind of review, we do some more conditional probabilities, and then we'll transition to kind of our next topic, finish out probabilities before next week we start looking at discrete random variables. Okay? So start working on that next Excel assignment. Otherwise, I'll see you guys on Friday.